This is problem 1 on exam 1 of module 4 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 1 is 3 capacitors are hooked up as shown in series. The values are 60, 30, and 60 microfarads. When a battery is hooked up across the entire circuit, the center capacitor has a voltage of 4 volts across it. Part A asks, what is the voltage of the battery? Part B asks, if the breakdown voltage of each of the 3 capacitors is 50 volts, how much voltage can be placed across the entire circuit before something starts to smell? A good diagram is essential to good problem solving. Let's label what we are given. There's a 60 microfarad here, a 30 in the middle, and a 60 over here, and we also know that the center capacitor has a voltage of 4 volts across it, right here. What now? How do we get the voltage of the battery? We know the voltage across the center capacitor, but we don't know the voltage drop across each of these, but maybe we can get there by getting the charge on the 2 outer capacitors. We know that C is Q over V for each capacitor individually. We have 2 of the 3 values for the center capacitor, so we can get the charge on it. C is Q over V. We know the capacitance is 30 microfarads, and the voltage drop is 4 volts. We can get Q. I wrote 10 to the minus 6 farads here, which is microfarads, and that results in microcoulombs. 30 times 4 is 120. And then we have the micro from the microfarads. The center capacitor has a charge of 120 microcoulombs. The battery can't get to this guy, it's not connected, so the charge this one gets must have come from this plate. So all the capacitors have 120 microcoulombs. It's crucial to understand this, so let's invest the time to do so. First, we'll put the battery in just for completeness. What does the battery do? The battery has access to this plate, and it sucks electrons from this plate and it forces them on this plate. The charging happens very quickly for all 3 capacitors. But for teaching, to understand what's going on, let's consider the charging in discrete steps. First, the battery pulls electrons from the right side of the capacitor on the right, this one, and puts them over here. That's the only thing the battery can do. So there we go. Now what happens? The positive charge here will attract electrons from this one. So electrons leave here and dead end over here. They'd love to go across, but they can't. It's a dead end. There's a gap there. So they end up piling up right here. When they leave, this has now become positive, electrons left. And at the same time, of course, the same thing happens over here. The electrons here repel the electrons in this plate. They run away towards this positive charge, and they reach this dead end. That leaves this side positive. So this is what we have. Of course, the charge here has to be the charge here because the electrons left this one, leaving that positive. There's no net charge anywhere. There's just charge separation. There's no net charge on the circuit. So if this is 120 microcoulombs of positive charge, this has to be 120 microcoulombs of negative charge. The total is neutral. It didn't start out with any charge. So now we understand that every capacitor has to have the same charge. So now we have the charge and the capacitance of the 2 outer capacitors, which means we can get the voltage drop. The charge is 120 microcoulombs, the capacitance is 60 microfarads. Each of the outer capacitors has a voltage drop of 2 volts. So now we can get the voltage of the battery. 2 here, 4 here, 2 here, that's a total of 8. The battery must be 8 volts. There are the 2's. 2 plus 4 plus 2 is 8. Now we can tackle part B, which involves breakdown voltage. I guess we're not. We're going to check our answer to part A by getting the equivalent capacitance of the circuit. What capacitance does the battery think is up here? You hook up the battery, it says, okay, positive charge one side, negative charge the other side. Let's calculate the equivalent capacitance of these three capacitors in series. They're in series, it's 1 over, so 1 over C equivalent is 1 over C1 plus 1 over C2 plus 1 over C3. Plug it in the values, getting a common denominator here, that's 2/60ths, plus 1/60th plus 1/60th is 4/60ths. Flip it upside down, and that's 15 microfarads. So the battery thinks there's a 15 microfarad capacitor up there, and the battery pumps 120 microcoulombs from one side to the other. The voltage of the battery is the charge that went through the battery, charge that the battery shuttled from one side to the other, divided by the equivalent capacitance. 120 microcoulombs is the charge, 15 microfarads is the equivalent capacitance of the whole circuit. The battery must be 8 volts. That's the same answer we got before. Good news. Okay, we're happy. Now we can tackle part B. Breakdown voltage. Good strategy is to identify the vulnerable capacitor. Which one's going to go first? And it's the middle one. The middle one has the highest voltage of any of the three. It's always twice as high as this, no matter what the voltage of the battery is. This guy's going to go first. It's going to get to 50 first. When it gets to 50, the other two are only going to be at 25. They're half as great. So if we make this a power supply and we start turning up the crank, when it gets to 60, it's still going to be okay, because this guy's not going to be at 50. Just like this guy's going to be at 30, and these guys are each going to be at 15. In order for this to get to 50, the power supply has to read 100. If this is 100, that's 50, that's 25, that's 25. The total voltage drop across the circuit is 100. The voltage drop across the middle one is 50. This one starts to smoke. So the answer is the breakdown voltage of the circuit is 100 volts. That's problem 1.